We talked about electrophilic addition reactions to double bonds. So we are adding molecules to double bonds. The double bond is going to be consumed, and then we are making a product that doesn't have a double bond anymore. So the name suggests it's electrophilic addition. So electrophile, whatever the things we're going to use, is going to be attacked by the high electrons. And then that could be central definitely to the proton. The H plus is a good electrophile. So if you add an HBr, the proton goes into the carbon first, but you really have to notice that which carbon is going to get the carbon cation. The stability of the carbon cation is very critical. So the proton goes the less substituted carbon, so that you get the more substituted carbon cation, and then that is a Markov-Nikov rule, right? And then the bromide capture the carbon cation will make the HBr addition product. And this is a Markov-Nikov products. So Markov-Nikov products, electrophile go to less substituted carbon, nucleophile goes to more substituted carbon. And then I'm going to repeat these things with another example later, so you understand why I'm emphasizing them. Maybe it's going through the today's materials. There's another way adding HBr that will be the radical condition. So HBr mixed together with the hydrogen peroxide or the even alkyl hydrogen peroxide, any of the combination, but the main thing is there will be oxygen single bond. That is not a really strong bond. So if you heat the solution, they break up, make an oxygen radical, start the initiation process. So in the end, you get the bromine radical produced first. The bromine radical is electrophile because the radical is electron deficient species. The pi electrons get the bromine first, not the proton first, like the HBr addition. So this time, bromine goes first. So you get the radical on the more substituted carbon. So regardless what are done, you get the most stable intermediate. That is the key. Bromine goes first because it's radical conditions. And then that will capture the hydrogen from HBr. Then you get the products, but you get the H and the bromine in opposite. So this is something called an anti-Markov-Nikov products. You really need to distinguish what product they are, because depending on what they are, you have to use different reagents. So that's why the Markov-Nikov products typically have the nucleophile substituted as more substituted carbon. And then the electrophile go to less substituted carbon. That's the features of the Markov-Nikov product. We also talk about the halogenation reaction. There will be chlorine molecules, bromine molecules, iodine molecules. That we really have to pay attention to what solvent the reactions are carried out. If they are done in the non-nucleophilic solvents, like a solvent that doesn't have lone pairs, like oxygen lone pairs or nitrogen lone pairs, something that we would consider non-nucleophilic solvents, and like a chloroform, dichloromethane, and then carbon tetrachloride, things like that. Then pi bonds attack the bromine or chlorine and kick the bromides out, but the halogens are much bigger than the hydrogen, so they actually make something called the bridged ion. Those bridged ion, so they make two bonds over the two carbons of those bonds. But the bromine is positive charges, so that's going to pull electron density from the carbon it bound to. But the more substituted carbon will lose more. And that is a really key thing that you have to understand. Three mechanisms will go through this way, and then even though they may have a different electrophile coming in, they just work the same way. The more substituted carbon will bear the more carbocation characters, and that's the one nucleophile. This time the left bromide is the one that come back and attack from the opposite side. So it's an anti-emissionist. So you get the bromine, that's from the bromine ion, and then you get the bromine, that's from the bromide, it looks same right now because they're all both bromine. But if you happen to mix it out of the profile, it'll show what goes where. So you really have to keep track of the what goes where. So, but anyway, you have to get a trace, not a sense. So this one, because the same elements going on, it really doesn't matter for the regional chemistry, but you really have to be specific for the stereochemistry. So that's when you do the halogenation in the non-nucleophilic solvents. But if you do the halogenation in a nucleophilic solvent like water, alcohol, things like that. I mean, alcohol, I put it there because you already have seen waters. It just works the same way. You got the halogen, basically make the bromine molecules, but this time you got solvent acting as a nucleophile. The solvent molecule is a lot of quantity. So solvent molecule makes an attack from the opposite side, so it's anti-addition again. And again, the more substituted carbon bears more carbocation characters. So that's the what solvent molecule makes an attack to. And then it opens up the brominium ion, lose the proton in the end. So you get the bromine on the less substituted side. And then the methoxy groups for the methanol sitting on the more substituted side. So I will call this product still follow the Markov nickel rule. I mentioned one more time, this is, I think, is a Markov nickel product because the nucleophile sitting on the more substituted side. I don't know how many times I repeat this thing, but if I'm repeating this many times, I really hope you understand why I'm doing this thing. I don't want to waste time, but I'm repeating so many times because that's the key to understand what reagent you're going to need to accomplish a certain things done. I mean, you're going to realize later. Anyway, so this is the haloform reaction, I mean, modified haloform reaction. But this is clearly something that we discussed, and you really have to understand these slides properly to move on. So that's what we discussed. So this is definitely different from the test 2. You see here is much more rich mechanisms. You have to analyze, where things go, how things goes, and then you have to apply them. So this will take more than what you have done for test 2. But the good thing is, it uses a different reagent. If you're adding HBr to double bond, it's H2 addition. It doesn't add water to that, right? Because it's HBr. If you're using a bromine in different solvents, it's like the reagent tells you what reaction it is. So at least it's a lot more easy to figure out what reaction will happen. But other than that, the concept actually getting broadened. And then you really have to still remember the things we discussed as 2, because that will be adding on to this. That will be the foundation of this. So don't expect the test 2 materials are not going to be appearing in final exam. They will.